On to question 6. Electrons are there in the Fe3 plus ion. So first, it might be easier to write down the electron configuration of iron and then the electron configuration of Fe3 plus. So first, let's recall that electron configuration of just a neutral iron atom is argon in square brackets, 4s2, 3d6. Okay, so when you have Fe3 plus, that means that 3 of these electrons were taken away. Since electrons have a negative charge, that means the iron now has a 3 plus charge. And it has a new electron configuration, which is argon 4s2. And then instead of 3d6, we're going to minus 3 electrons. And it is now 3d3. So, change the color. I can draw out an orbital filling diagram. Just showing the 4s orbital and then the 3d orbital, which will roughly look like that. And now I'm going to fill in my electrons using these arrows. So that's 1 electron, that's 2 electrons, and now I need to draw in 3 more. So 1, 2, 3. Okay, so now just looking at the diagram, we can say that there are 3 unpaired electrons. So we can say that this is paramagnetic. If there were no unpaired electrons, it would be diamagnetic. Okay, so the junior tutor said there are 3 unpaired electrons in Fe3+. For this problem, we can determine the answer by determining the electron configuration of the ion, or atoms. Electron configuration notation consists of a sequence of atomic subshell labels with the number of electrons assigned to each subshell placed as a superscript. However, for atoms with many electrons, these notations can be lengthy, and so an abbreviated notation is used. Electron configuration can be visualized as the core electron equivalent to the noble gas of the preceding period, so in our case it was argon, and the valence electrons. Each element in a period differs only by the last few subshells. So this is a way that helps people write down the order of electron configurations. From 1 to 7 is the S, and then 2 to 7, you can see this is P, and then 3 to 6 is D, and then 4F, 5F, and then you kind of just go diagonally like this. So the order would be 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, and so on and so forth. So this S subshell will have a maximum of 2 electrons, the P max of 6, D has a max of 10, and F has a max of 16. The electron configuration need not be written as a whole. It can be shortened using the condensed electron configuration. Yep, so they have an example for magnesium, which is here on the periodic table. It has an electron configuration of 1s2, 2s2, 2p6, 3s2. But the condensed version of it, you write down the noble gas that comes before it, so in this case it's neon, and then just 3s2. Yep, so this is the way that I do it for writing electron configuration, just by looking at the periodic table, because usually these are given to you in an exam. So they have here all the different orbitals labeled S, P, D, and F. And then you just kind of move across the periodic table in order like that. In the problem, the ion being asked is Fe3+, since it has a positive charge from the ground state Fe iron atom, loses 3 electrons, and this will also be accounted to the electron configuration. Okay, so they got argon 4s2, 3d3. Using Hund's rule, which states that all the orbitals in a subshell must be singly occupied first before any orbital is doubly occupied, positioning of the 3 elements in the last subshell can be determined. Since there are 5 orbitals in the D subshell, there are only 3 electrons. These 3 electrons will fill up an orbital each, and thus there are 3 unpaired electrons. Yep, so this solution is correct. Yeah, there. Could write 2 more. Doesn't. Yep, so the solution is correct. Great explanation. Okay, so on my end, I just added 2 extra orbitals in the 3D subshell, but that doesn't change the answer. There are still 3 unpaired electrons.